Here we have another batch of examples where we're evaluating logarithms, getting practice with our definition of a logarithm. We've seen it several times now and worked with it. Y equals log base b of x is the same thing as b to the y power equals x. We've got a base b to a power y is equal to a result that we'll call x. On the logarithm side, on the left, we've got the power y equal to log base b of the result, x. If you haven't watched my other videos, make sure you go check them out. The videos prior to this set of examples. Watch those sequentially to make sure you get all the right ideas going in your brain. But now let's tackle these. Not necessarily in order, but we'll start with question number 11 here, and we will evaluate log of 1,000. We recall from one of our previous examples that if we have a logarithm with no base written, then that's log base 10. We call that the common logarithm, log base 10, because we got 10 fingers and 10 toes. We count by tens. We have a decimal base 10 system, so that's the common logarithm. Log base 10 of 1,000. We have a base 10 to some power gives me a result of 1,000. Of course, well, you can verify that 10 to the third power is 1,000. So my power, my logarithm, my answer is 3. 10 to the third power is 1,000. For question number 12, we've got log base 10 of 100 to the 8th power. The question is, what power of 10, 10 to what power gives me 100 to the 8th power? Doing a little bit of work with exponents, we find that the answer is 16, because 100 is 10 squared, and 10 squared to the 8th power is 10 to the 16th power. So what power of 10 is 100 to the 8th power? It's a 16th power. A logarithm is a power. That logarithm then is equal to the power 16. In question number 13, we've got something a little bit different, but it turns out to work just fine. The question is 10 to the power of log 31. Now consider this, that I don't think anybody's going to argue this. Log 31 is equal to log 31. Okay, that tells me that, let me switch up my colors a little bit here, that if I have a base 10 and I translate that over here to a base 10 logarithm with a power of log 31, a power of log 31 translates to a result of 31. That's a little different. That's a little more involved than the examples we've looked at so far. But if you look carefully at the definition of a logarithm that says we have a base, in this case a base of 10, to a power, in this case of log 31, is equal to the result 31, then log base 10 of the result 31 is equal to the power log of 31, and that's just log of 31 equals log of 31, and that is true. Perhaps a more simplified and useful, frankly, way of looking at this is going back to our first example where I mentioned that logarithms and exponentials are opposites of each other. They're inverses of each other. I have convinced myself mathematically that this number 31 is the right answer. A way that we can consider simplifying this, this logarithmic expression is that a base 10 exponential and a base 10 logarithm, they're opposites, they're inverses. In effect, they cancel each other out, and I'm just left with 31. The base 10 exponential and the base 10 logarithm are inverses, they're opposites. Like a radical and a power, they cancel each other out. Like addition and subtraction, they cancel each other out. And we're just left with, in this case, the number 31. Something similar happens in question number 16. We've got a base E exponential with a natural logarithm that is log base E, as you read and noted in your pre-class work. We've got a base E exponential and a base E logarithm that end up canceling each other out, and our answer is 1537. Those two, both of those, 13 and 16, are examples of how logarithms and exponentials are going to work together, in a sense, work against each other, so that we can solve these exponential and logarithmic functions and equations as we go forward and into applications and word problems in future modules in this class. Actually, somewhat similarly, question number 15 has a logarithm, base E, with a base E exponential, and so it shouldn't surprise us terribly to hear and learn that the answer is 4, because a base E to the power 4 gives me a result of e to the 4th, because e to the 4th equals e to the 4th. That works mathematically. It satisfies the definition. You can think of it a little more simplistically as the log base E here and the base E exponential that it goes along with cancel each other out. They're inverses, and my answer is just 4. Finally, we have in question number 14 the natural log of 500. That's log base E of 500. That's asking us base E to what power gives me 500? And 500 is not a power of E. That's a problem. 500 is not a power of E. So when we run into a wall here where we have a result, in this case 500, that is not a power of the base, in this case E, well then all we can do, if we must evaluate the logarithm, like say this is an application problem and I need to figure out what the natural log of 500 is in order to answer and interpret my answer for a word problem, then all we can do is plug it into a calculator. And that's okay in case we need to get that answer to interpret it in, say, a word problem. And the instructions will be clear as to when you're expected to use a calculator or when you're expected to show your work and talk through your reasoning, as I've done with all of the others here, to give the correct simplified answer. In this case, though, I find that the natural log of 500 is approximately 6.2146 because e to the 6.2146 is almost exactly 500. And of course, you got your powers of e memorized. You know that e to the 6.2146, you know that that's 500. No, I'm kidding. I'm kidding. But you could use a calculator to verify and must make sense of these facts. Even if it's just verifying, seeing it works both ways in a calculator, you can start to make the connections between the two forms, that's valuable. All right, there's another string of examples of evaluating logarithms. We'll move on in our next video, talk some more about logs.